This short slideshow will explain how volcanoes actually erupt, a topic that is not covered in great detail in your textbook. You will find that the style of eruption depends mostly on the fate of bubbles that spontaneously form in the magma as it ascends. When these bubbles can escape easily, quiet lava flow eruptions are produced. But when the bubbles are trapped in the magma, they increase in pressure until they finally blast their way out, producing a violent eruption full of pyroclasts. Eruptions start when the magma being stored in the underground magma chamber breaks through the rigid lid that was holding it in place and begins to rise to the surface. The magma rises because it is less dense than the surrounding rock. One of the most important properties of the magma that controls its ascent is its viscosity. Viscosity is a measure of the stiffness of a fluid. Fluids like tar have a high viscosity, while other fluids like water have a low viscosity. You're probably familiar with the term viscosity because it's used to characterize motor oils, which are frequently advertised on television. The SAE number of a motor oil, for example SAE 30, is a measure of its viscosity. So a motor oil labeled SAE 40 has a higher viscosity than a motor oil labeled SAE 20. Incidentally, the common mixed grade designations like 10W40 are used to describe both the cold viscosity of motor oil and the high temperature viscosity, which we don't have to worry about here. The viscosity of any fluid is determined by two important factors, temperature and composition. The effect of temperature is pretty obvious if you've ever tried to pour chocolate syrup straight from the fridge. Just a few seconds in the microwave, however, and it flows easily because its viscosity decreases dramatically when it's hotter. Temperature decreases the viscosity of all fluids, including magma. For magmas, the key ingredient in the composition that affects the viscosity is the amount of silicon. Remember, in rocks and minerals, silicon is always found in the center of a silica tetrahedron, and the silica tetrahedra are usually linked together into chains, sheets, or other shapes. This is also true for magmas, but the linkages aren't as regular and tend to produce ragged chains of varying lengths. So here's how it works. Magmas that have a lot of silicon, like silicic magmas, tend to create a lot of long silica tetrahedra chains. These chains get tangled up with each other when the magma tries to flow, making flow difficult. In other words, the chains cause the magma to have a high viscosity. Magmas with less silica, like mafic magmas, also produce chains, but the silica tetrahedra chains are fewer in number and shorter. This means that they don't get as tangled when the magma tries to flow, so the magma flows more easily. In other words, the shorter chains cause the magma to have a lower viscosity. There's one more factor that affects the viscosity of magma, but it's not as important as the first two. It's the amount of dissolved volatiles, or substances like water or CO2 that are gases on the surface. These dissolved gases like to link up with the silica tetrahedra chains, preventing them from joining with each other to produce longer chains. As a result, the volatiles keep the chains short and thus keep the viscosity low. So in conclusion, the more silica, the more viscous the magma. You would expect silicic magmas to have a high viscosity and mafic magmas to have a low viscosity. A lot of gas dissolved in the magma will tend to reduce the viscosity somewhat, but this effect is pretty minor compared to the effects of temperature and composition. Volatiles, however, play a key role in the style of volcanic eruptions because they usually end up coming out of the magma and forming a separate vapor phase. In other words, bubbles. In order to understand why this happens, you need to know something about how bubbles are dissolved in magma and how this changes with pressure. Here's the key point. The amount of a gas that can be dissolved into a magma is proportional to the pressure. More pressure, more dissolved gas. We can show this on a solubility diagram like the one shown here, where we plot the pressure on the x-axis versus the percentage of dissolved gas on the y-axis. The red line is the solubility curve, and notice it increases up and away from the origin. This means that the percentage of dissolved gas at high pressure is more than the percentage of dissolved gas at low pressure. We use the term undersaturated if the liquid contains some dissolved gas, but not as much as it could possibly contain. Any composition that falls in the yellow area on the diagram will be undersaturated. The red curve represents the maximum amount of gas that can be dissolved in the liquid at any pressure. When the liquid contains exactly this amount, no more or no less, we say it's saturated. When there's more gas than can be dissolved into the liquid, then there will be gas left over. This gas forms a separate vapor phase, which usually occurs as bubbles dispersed in the magma. So let's see what happens when we have 10% gas and we try to dissolve it into a liquid. In other words, suppose we had 100 grams of liquid and 10 grams of H2O water vapor. Where does that gas go? At low pressure, the liquid can't dissolve 10% gas, not even close. It maybe can dissolve only 3% gas, and the leftover gas remains as bubbles. As we increase the pressure, more of the gas can be dissolved in the liquid, so some of the bubbles disappear as they are dissolved. But there's still more gas than saturation, so some bubbles remain. Finally, at the highest pressure, all 10% of the gas can be dissolved in the liquid, and there are no more bubbles. So now let's apply what you've just learned to volcanoes. Remember, eruptions start when magma rises under a volcano. As the magma rises, it experiences lower and lower pressures because there's less stuff on top of it pressing down. So we ought to see the exact same thing we've just shown on the previous slide, except in reverse, because the pressure is decreasing, not increasing. To see an animation of what happens, just click on the blue box. Notice that as the pressure decreases, the magma first reaches saturation, and beyond that just produces more and more bubbles because less and less of the gas can remain dissolved. That's what it looks like in the lab. Here's what it would look like in the Earth. Click on the blue box to see an animation of a little blob of magma rising. As it rises, the pressure decreases, and as the pressure decreases, the solubility of volatiles also decreases, driving the volatiles out of solution and forming bubbles. Believe it or not, this is just another form of boiling. The magma boils as it rises because the solubility of gas decreases, forcing bubbles to form. The next question is, what happens to those bubbles? The answer to that question determines whether the eruption will be quiet or loud. There are two important laws of physics that decide the fate of the bubbles. The first is Boyle's law, which is part of the ideal gas law. It simply says that at constant temperature, the product of pressure and volume of a gas must be constant. This means that if one increases, the other has to decrease, and vice versa. As the magma rises under the volcano, its temperature remains nearly constant, so Boyle's law applies. This means that as the pressure decreases, the gas bubble wants to expand. However, the ability of the bubble to expand depends on the viscosity of the surrounding magma. If the magma has a low viscosity, it can easily flow out of the way when the bubble presses against it, and the bubble can expand without difficulty. Click on the red box to see what happens when a bubble tries to expand in a magma with a low viscosity, one we might term runny. As the viscosity of the magma increases, the bubble finds it increasingly difficult to push the magma out of the way and expand. When the magma is relatively viscous, the bubble can expand, but not as much and not as fast. Click on the orange button to see what happens. What happens when the viscosity of the magma is ultra stiff? Real silicic magmas have viscosity stiffer than road tar. When a bubble tries to expand in this kind of magma, it basically can't. The magma is just too stiff and won't flow out of the way. Instead, the magma traps the pressure it had when it was deep underground and seals it inside the bubble. Click on the blue box to see an animation of this process. Since we can't easily show an increase in pressure of the gas, I've just changed the color of the bubble to orange. This indicates that it's being pressurized. The second physical law that determines the fate of the bubbles is Stokes' law. Stokes' law is usually called Stokes' settling law because it describes the rate at which things settle out of a liquid. But it actually can be used to describe the rate at which any object moves through a fluid with a different density. And if the density of the object is less than that density of the fluid, like a bubble, it will rise. Stokes' law simply says that the rate of rise of the bubbles depends on the viscosity. This ought to make sense. Just like with expansion, the bubble can only rise if the magma accommodates it by moving out of the way, and the viscosity describes how easily the magma can do that. Again, click on the buttons to see how bubbles rise in runny, viscous, and superviscous magmas. Notice that in the superviscous magma, the bubble doesn't move at all. It just sits there with the pressure increasing. Here we put it all together. The magma rising, bubbles forming as the pressure decreases, and then the bubbles expanding and rising if they can. Click on the blue boxes to see the difference between a runny mafic magma and a very viscous silicic magma. Can you see the difference? There's actually one detail I've left out to this point. The magma rises because it's less dense than the surrounding rock, and the speed with which it rises depends on that density difference. When the magma is much less dense than the rock, it rises faster. When it's just slightly less dense than the rock, it rises more slowly. By magma, here we mean the entire contents of the liquid that's rising through the cracks under the volcano, which includes any crystals and any bubbles that may exist. And since the bubbles have such a low density, their appearance dramatically lowers the density of the magma, causing it to accelerate. So as the bubbles form, the magma picks up speed like a runaway train rushing to the surface. Click on the blue button to see the runaway train. So what happens next? One of two things. If the magma is runny, then the bubbles that form will efficiently rise to the surface and gently escape through the top. The magma will seep out of the ground gently, producing lava flows. This kind of eruption is pretty cool to watch, but not very dangerous. You can see a simulation of this eruption by clicking on the red box. If instead the magma is very viscous, and especially if it also contains a lot of gas, then the eruption is very different. The bubbles form, but they can't expand and they can't escape, so they simply sit there with their locked-in pressure riding along with the magma to the surface. Meanwhile, the pressure of the surrounding liquid decreases as usual, producing a giant pressure difference between the bubbles and the magma in which they're embedded. Eventually, the bubbles simply blast their way through the viscous magma, shattering it and throwing it high into the air. This is the very definition of an explosive eruption. Click on the blue box to see an animation of this type of eruption.